Good morning, everyone. My name is Yueyang Lu, and today I'll be walking you through milestone 1 of the AetherMart Foundational Database project. My goal for this milestone was to build a reliable, secure, and functional data foundation for the AetherMart, and I'm excited to share my progress. First, let's talk about the environment. I established a robust environment on the AWS using an EC2 instance to host my MariaDB database server. For security, network rules were configured to allow administrative access through secure SSH on port 22. These screenshots show that the MariaDB is successfully installed and port 22 is opened. The schema was designed to ensure both data integrity and efficiency. The schema is normalized to reduce data redundancy through the use of foreign keys, such as category ID in the product table. To further ensure the data is accurate and trustworthy, the design utilized unique and tight constraints. This ERD illustrates the relationships between 7 key entities in the database and is used to design foreign key functions in the schema. These slides show the SQL codes for table creation. Before data initial ingestion, I use FileZilla to securely transferring the 7 source CSV files from a local machine to the AWS server, and the dataset I was using is set1. Before loading, I identified several data quality issues in the source files. These included commas in supplier names and duplicate rows, blank email files for customers, multiple inconsistent date formats in the orders table, and non-numeric ratings in the reviews data. Solution summary for each are listed and will be explained in the details later. I chose the ELT method to keep all the raw data. The initial data loading was performed by taking the raw data from all 7 CSV files and loading it into corresponding staging tables using the load data infile command. This method was selected because it is significantly faster than performing row-by-row insertions. To manage potential data inconsistencies during the load, several strategies were employed. First, flexible data types. Any column with non-formatting issues was identified as generic text type in the staging table, which allows the database to accept any value without reading an error. Second, duplicate rows. All rows were loaded without checking for uniqueness, with the plan that the application will be handled in the later step. The following 2 slides go through the SQL codes for initial data ingestion. These screenshots show that all raw data, regardless of format issues, are successfully loaded into staging tables. SQL codes for data transformation are shown here. For duplicated records in the suppliers table, I only keep 1 record. For blank customer emails, they are turned to null values to pass the unique check in the schema. Date formats are corrected by screening over multiple possible format types. Invalid ratings in the reviews table are turned into null values, and the dates are corrected using the same method as the ones in orders. The following screenshots shows how the wrong format data in previous tables are turned into correct formats after the transformation. To enhance the database functionality, I implemented several advanced SQL features. First, I created views such as customer order summary and product sales summary to provide pre-joined simplified tables for easy reporting. Also, I added a virtual column called full name to the customers table, which automatically combines the first and last name, simplifying queries. Third, I also built a stored procedure, get product revenue, to create reusable and secure way to calculate revenue for a specific product. And finally, I created a user-defined function, get customer total spending, to easily calculate a customer's total spending with a query. The following slides go through the SQL codes used to create these functions. These screenshots show that views, virtual column, stored procedure, and user-defined function are all successfully implemented to the database. A comprehensive role-based access control system was implemented to ensure users can only access the data they need for their job function. Least privileges principles are applied to the design. The following key roles were created to manage permissions. First, this role has full administrative privileges. The second is app rewrite role. This role is for general application access with select, insert, and update permissions. The third is product manager role. This role provides read-only access to products and categories. The final one is customer service role. This role has view and update access for customers and others. The following slides go through SQL scripts for user role and permission setup. This slide shows the verification of a role-based security control through an example of a product manager. She first needs password to access the database and do not have permission to update a product price or insert a new product. In conclusion, I have deployed a secure MariaDB database on AWS EC2, implemented a robust relational schema, executed a full ELT process to load and cleanse the core data, create functions with advanced features, and established a secure role-based access system. I used Google Gemini to accelerate the initial drafting of code and outlines. It was excellent for explaining error messages and suggesting solutions. The main limitation was the lack of context. For example, when creating database roles, it initially gave generic permissions like read and write instead of business-specific roles like product manager. A key takeaway was to leverage different AI models when debugging, as relying on a single model can sometimes lead to less effective solutions.